This is part 7 in our series of lectures on other forms of induction. And in this lecture, I'm going to show you yet another application of the principle of complete induction. I'm going to show you how to prove a rather important theorem known as the division algorithm. Before I do that, I wanted to mention that we spent quite a number of lectures studying limits of functions and limits of sequences using those epsilon and delta definitions of those things. And that was intended to show you a little bit about a branch of mathematics which we call analysis or advanced calculus. And in the next few lectures, I'm going to show you a little bit about a branch of mathematics called algebra. And the division algorithm and some of the things that we're going to look at subsequently are parts of the subject of algebra. So you might revisit this if you take a course in number theory 301, or if you take an abstract algebra course, Math 321. These are things that you would see in those courses. So here's a statement of the division algorithm. It says that if you give yourself any two integers a and b, if a is not equal to 0, then there exist integers q and r such that I'm able to write b in the form aq plus r, where r satisfies this inequality, that it's bigger than or equal to 0 and strictly smaller than the absolute value of a. Furthermore, q and r are unique. So in the theorem, we refer to a as the divisor, q is known as the quotient, and r is known as the remainder. So this is something that's very familiar to you. It's saying that you can divide a into b and be left with a remainder of the appropriate size. It's the fact that we're specifying the size of that remainder that makes q and r unique. Well, even though the theorem may seem completely obvious to you, it still requires a proof, and it's going to make use of some of the tools that we've already developed in order to prove it. We're going to make use of the principle of complete induction. So let me first show you the proof of the existence part of the theorem. The uniqueness part of the theorem is actually quite simple, and we'll leave that for the last page of this lecture. But for convenience, and in order to avoid too many technical details, because I don't really want to cloud the issue with too many ideas here, I'm just going to show you the proof in case a and b are both natural numbers, even though the theorem is true in greater generality than that, when a and b are not necessarily positive. So what we're going to do is we're going to fix an a in the natural numbers, and we're going to do everything relative to that a. We're essentially going to prove the rest of the theorem by induction on the other variable, the b in the theorem. So in order to apply principle of complete induction, we need a set S, which we're going to try to prove is equal to the whole set of natural numbers. So we take S to be the set of all natural numbers b for which the conclusion of the theorem holds. In other words, for which there exists integers q and r, such that we can write b as aq plus r, and r satisfies this inequality here. We're going to prove that S is equal to the set of natural numbers as an application of the principle of complete induction. In order to do the basis step, in order to see that 1 is an element of S, I'm going to split it up into two cases depending upon if A is equal to 1 or if A is bigger than 1. If A is equal to 1, then we're able to write 1 as 1 times 1 plus 0. So we can simply choose our q to be this 1 here. We can choose the r to be 0, which is certainly going to satisfy this inequality here. And so that takes care of the case where a is equal to 1. If a is not equal to 1, that means a is bigger than 1. Then we can write 1 as 0 times a plus 1, and this 1 is smaller than a, so we can choose our q to be 0 and our r to be 1, and that will satisfy the conditions of the theorem. So that means we've shown in any case that 1 is an element of S. So that's the end of the proof of the basis step. Now we come to the inductive step. We give ourselves a B, a natural number B, and we suppose that B is bigger than or equal to 2, and all of its predecessors lie in S. We take 2 here because that's the first natural number for which we haven't already established that it's in S. So our task is then to show that we can deduce B as an element of S. We're going to consider 3 cases: the case where B is smaller than A, equal to A, and bigger than A. And the cases where B is smaller than A and equal to A, those are sort of the trivial cases. The hard case is where B is bigger than A. That's the one where we're really going to have to use the inductive hypothesis. If B is smaller than A, well then we can write B as 0 times A plus B. And since B is smaller than A, we can choose our Q to be 0 and our B to be, and our R to be B, and that works. If B is equal to A, we can do a similar thing. We can write B as 1 times A plus 0. And so that works where we pick Q equal to 1 and R equal to 0. The most interesting case is the one where B is bigger than A. In that case, you see B minus A is now positive, and it's a natural number, but it's smaller than B. So that means it lies in this set here, and that means B minus A must be an element of S. That's the inductive hypothesis. And since B minus A is an element of S, that means that there exist integers Q and R, such that I can write B minus A as AQ plus R, where R satisfies these inequalities. Now we just simply transpose this A term to the other side, and we get this. Well, now we've managed to write B as an integer multiple of A plus R. It's the same R as before, and that's exactly what it means to say that B is an element of S, and so that completes the inductive step. So it follows from the principle of complete induction that S is equal to N, a set of natural numbers. So finally, let's look at the proof of the uniqueness part of the theorem, but that's actually quite simple. So here's the proof. So what it means is we start with our integers A and B, and by the way, this is the complete generality. I'm not assuming that A and B are natural numbers this time. We don't have any difficulty proving the general case of the uniqueness. Suppose that one can write our B in 2 different ways, as AQ1 plus R1 or as AQ2 plus R2, where R1 and R2 satisfy these inequalities that the theorem asks for. So what we have to do is we have to prove that Q1 and Q2 are equal and R1 and R2 are equal. That's what uniqueness means. So what we do is we take this equation and we move the AQ2 term to the left and we move the R1 term to the right, and that gives us this, after we factor the A out. Now R1 and R2 both lie between 0 and absolute A. And so without loss of generality, one of them must be bigger than or equal to the other. It doesn't really matter which one. So let's just assume that it's R2 that's bigger than or equal to R1. It really doesn't make any difference which one of the two is bigger. So now, if it were true that R1 is not equal to R2, then this is a positive number, and that would say that A divides R2 minus R1, right? Because A times this integer is equal to R2 minus R1. But in order that A divides R2 minus R1, A would necessarily have to be smaller than or equal to R2 minus R1. But that's impossible, because the fact that R1 and R2 both lie between 0 and absolute A means that their difference must be strictly smaller than absolute A. And that contradicts the fact that A is dividing R2 minus R1. And therefore R1 has to equal R2. And the moment you deduce that R1 equals R2, that means that this is 0. So this must be 0. And A isn't 0, so that means that Q1 must equal Q2. And so we've got the uniqueness. We've deduced that R1 has to equal R2 and Q1 has to equal Q2, and so that completes the proof. I'd just like to close by saying that the division algorithm is quite a useful result in algebra, and I expect you to know the statement of the theorem from memory. So make sure you learn the statement of the theorem very well. In fact, we're going to make use of it in the next few lectures.